Okay, we had left off, we had just talked about the ideal gas law and the related combined gas law. We said we're going to start doing a bunch of calculations with those. One concept that's related to gas laws is the idea of partial pressure. So for a given mixture of gases, we said gas pressure is caused by particles bumping into things. Well, if you have a mixture of gases, then different kinds of particles are bumping into things. And so the pressure caused by just one kind of gas particle is what's called the partial pressure of that gas. All right. One thing I want to point out is that there's no such thing as partial volume of one component of a gas mixture. Why is there no such thing as partial volume? Because all the particles are spread out inside the whole container. So you can't say in this room, oh, 80% of the gas in this room is nitrogen and about 20% is oxygen. And so the oxygen occupies this 20% of the volume of the room, and the nitrogen occupies that 80% of the volume of the room. That would be bad for us, because then we'd all have to huddle together in the part where the oxygen was. So I do want to point out there's no such thing as partial volume, and for that matter, there's no such thing as partial temperature either. We wouldn't say that the oxygen in this room is at, I don't know, 70 degrees and the nitrogen in this room is at 30 degrees. That just wouldn't happen. So temperature and volume apply to every gas in the mixture. Thing I want you to know about partial pressure is the partial pressures of all the individual components will add up to the total pressure. So for example, for air, the total pressure is going to be the pressure of nitrogen plus the pressure of oxygen plus the pressure of argon. There's a little bit of argon in air, plus the pressure of the water vapor. And then there's a tiny bit of CO2. I'm just going to say pressure of other trace gases. So there's too many to list, but these are the main components. So we can have partial pressure. We use this concept a lot. It's a way to mentally separate the components of a gas. Now, because volume and temperature apply to everything in the mixture, but pressure doesn't, you might ask, well, what about number of moles? Well, we can have different numbers of moles of the gases. Do you have another slide? Oh. I was supposed to have another slide where I was going to say you can apply the ideal gas law to an individual component. I'll just add it here. So you can apply the ideal gas law to individual components of a mixture. So we could say the partial pressure of any gas in the mixture. So let's say the partial pressure of O2 times the volume will equal the number of moles of O2 times R times the temperature. So when you use the ideal gas law for individual components, the only thing that's specific to the individual component is pressure in moles, whereas volume and temperature are the same. So we'll use the ideal gas law a lot to calculate, well, what's the partial pressure of such and such in this situation? If we know the number of moles and the volume and the temperature, we can get its partial pressure. Okay. So we'll do some problems with that. All right. So now on to a conceptual idea, and that's the idea that, all right, gases don't always follow the ideal gas law. The ideal gas law is actually based on a few simple assumptions. We'll talk about those in a moment. But gases don't always behave ideally. And we give them the unfortunate name real gases when they don't behave ideally. The reason I don't like that name is it's misleading. 90% of the time in the real world, gases do behave ideally. They do follow the ideal gas law most of the time. Then there are cases where they don't follow the ideal gas law that are less common. So I don't like the idea that we say, well, now it's a real gas when that's actually more the exception than the rule. What I want you to know is assume gases are ideal unless you're told otherwise. So there are two assumptions that the ideal gas law is based on. One is that the gas particles should feel negligible attraction for each other. And another is that the particles have to be far enough apart that we assume they're just little points in space and we ignore the volume that the molecules themselves take up. Now those two things actually hold pretty true most of the time, but there are times when they break down, and so when those break down, then the ideal gas law doesn't work. Okay? So let's think about when a gas is more likely to break the ideal gas law. So think about high temperature. What does it mean to say a gas is at high temperature? High temperature doesn't necessarily mean they're spread out. What does it mean? All right, so they have high kinetic energy, so they're moving fast. So if they're moving fast, let's think about how that affects these assumptions. They're moving really fast. Does that affect how far apart they are? It might indirectly, but not directly. It only affects how far apart they are if we're talking about, well, that makes the volume expand. But for a given volume, the temperature isn't going to affect that. What about the attractions? And here, I'll go to an analogy because that's what I do. I like analogies. Let's say you're walking down the street and you happen to pass someone you find attractive. What do? You might slow down. You might stop and say hi. You might chat them up. Depends, how shy you are and whatnot. What if you're driving down the highway and someone is driving the opposite direction down the highway who you happen to find attractive? What happens? Nothing. You keep going. You're going fast. You don't have time to notice each other. So when particles are moving quickly, they have less time for that attraction to actually cause a change in their behavior. So particles spend less time interacting. And so their attractions are more likely to be negligible. Student question is, what is negligible? Negligible means small enough to ignore. So negligible small enough to ignore. So if the attractions are more likely to be negligible, that means at high temperature we would expect gas behavior to be more or less ideal. More ideal behavior. Yep. Oh, sorry. There was a word left off on the notes here, and I don't know why. It was also negligible. It's another one that makes me feel like I'm saying roll juror. All right, so the question is, what's the cutoff for being negligible? And the answer is there's not a hard and fast cutoff. It's things behave ideally up to a certain point, and then like they start to deviate from the ideal gas law. So when you do problem set 9, you'll see there's a question that asks you to reason about this. It shows temperature and pressure and how the behavior changes. And so you're right. It's a continuum of, perfectly ideal means the ideal gas law works exactly. You calculate, if you know 3 of the variables, you calculate the 4th, and it's always right. Or if you take PV divided by NT, it's always equal to R. That's perfectly ideal behavior. What you see is, as you start to modify conditions, it won't always be constant. And there's not a simple cutoff I can give you. All right. So behavior is more ideal at high temperature. Now, what about low pressure? So low pressure, what does that mean about the gas particles? They're going to be more spread out now. All right. As you increase pressure, the way to increase pressure is to squeeze things close together. So at high pressure, you're allowing things to separate more. So low pressure gas particles are going to be more spread out. If they're more spread out, what does that mean about the amount of space they take up and about how often they're interacting? They interact a lot less, and the volume that they take up, that the molecules themselves take up, is going to be even smaller than the space between them. So there's going to be less interaction and more space between molecules relative to the size of the particles themselves. So at low pressure, both of those assumptions are more likely to be met. So behavior will be more ideal. All right. So if you're thinking about when a gas is likely to deviate from the ideal gas law, it would be at low temperature and high pressure, which makes sense because those are both conditions where a gas is more likely to turn into a liquid. So it starts behaving less like a gas. Now, if we're talking about the molecules themselves, what can we say? If things have strong intermolecular forces, is that going to make it behave more or less ideally? Less ideal because now when the particles get close to each other, they'll be attracted. And the thing is, the ideal gas law is based on this assumption that when they hit each other, they just bounce off. Now, if the particles are attracted to each other, what that does is it causes them to slow down as they pass each other, and it's going to cause them to pull in a little bit. So the volume that you would predict, or the actual volume, will end up being smaller than what you might predict because of the attractions between particles. And then, if you have big molecules versus small molecules, would big molecules be more or less likely to be ideal? Less likely. So big molecules are less ideal. So if you really want something to illustrate the ideal gas law, what would be a great choice of gas? Helium, hydrogen, those are both going to behave ideally the vast majority of the time. All right. Questions about ideal versus non-ideal? Good. So now, the last part that we're going to talk about is the motion of molecules and some processes that are not sort of just static measurements like pressure or temperature. Sorry. Not just pressure or temperature, but things where the gas has to move from one place to another. And so we'll talk about two processes known as diffusion and effusion. Diffusion is defined as gas spreading out from an area of low concentration to high concentration to low concentration. I don't know if I gave myself room to define that. On the next slide. All right, diffusion. Would be particles spreading out from high concentration to low concentration. And effusion would be particles escaping their container through a small hole. They like my yeah, yeah, right. All right, so these are two processes that are going to be governed by how fast particles move. Okay, so instead of using the ideal gas law, which just tells us about the pressure and the volume and the number of moles, what we need to consider now is how much kinetic energy they have. Okay. So what are the two factors that you can think of that'll affect how fast a given gas particle is moving, or a given collection of gas particles moving? All right, temperature is one of them. So remember, high temperature means high kinetic energy. And there's another one. Pressure actually doesn't affect how fast they're moving. But temperature tells us about their kinetic energy. There's another component that goes into kinetic energy besides velocity. Mass. So for a given kinetic energy, heavier particles actually move more slowly. So the question is, I thought things with larger mass have more kinetic energy. True, if I am moving at a certain velocity and a truck is moving at a certain velocity, the truck has more kinetic energy than I do. But if a truck and I are both moving with the same amount of kinetic energy, I have to be moving a lot faster to have the same amount of kinetic energy. Okay? So there's a relationship. Kinetic energy is 1/2 mv squared. So I can solve that for velocity. And let's see, I get 2ke equals mv squared. I get 2ke over m equals v squared. And then finally, velocity is going to be equal to the square root of 2ke over m. So remember, kinetic energy, we measure the average kinetic energy by temperature. And then for the mass of particles, we can think about the molar mass. So what this tells me is, at a given temp, exactly what I just said, at a given temp, lighter particles will be moving more quickly than heavy particles. So their average velocity is going to be proportional to 1 over the square root of their mass. In other words, lighter particles move faster. Which means that lighter particles are going to diffuse faster, or they're going to effuse faster. So in the interest of time, and because we don't do a lot of calculations with this anymore, I don't even think it's on your... Actually, can I see a formula sheet for a minute? See one right there. Yeah, it's no longer even on the formula sheet. But you can derive, just from this equation, something we call Graham's law. From what we had on the previous slide, you can derive the rate of effusion of gas 1 over the rate of effusion of gas 2 is going to be equal to the square root of the ratio of molar mass of gas 2 divided by molar mass of gas 1. Well, capital M, like in cursive, is molarity, and capital M another way is molar. Yeah, it's um, I wouldn't worry about it because this formula has been taken off the formula sheet, so don't worry about doing calculations with it. Um, but it's known as Graham's law of diffusion. What I would worry more about is just qualitative examples. Um, so the example on that last page, rather than solving it mathematically, which we could do, um, I just want to ask if you have. I'm gonna skip that one for a second. No, never mind. I'll do this one. Sorry, it's been a stressful day. Um, so let's say I have a mixture of oxygen gas, nitrogen gas, and neon gas. If there's a little tiny leak and you wait for a while, which one is going to come out the most quickly? Talk at your table. All right, I need an answer. Which one's fastest? Neon. All right. Why is neon the fastest? All right, so lightest equals fastest. And if you wanted to calculate the ratios of how fast they escape, you could do that, but I'm not worried about you doing those calculations. Um, Another interesting problem is on that last page. If you mix ammonia gas and HCl gas, when they meet up, they make ammonium chloride, which is an ionic solid. So if you start with a tube and you have ammonia at one end and HCl at the other end, and just let them move through the tube until they meet, you're going to see a solid ring form somewhere on the tube where they actually come together. So without calculating this, let's just estimate where we expect the ring to form. I mean, what would be your first estimate without even considering anything? What would be the first place you think of that they would meet? Right in the middle. So like our first estimate would 6. And then we want to consider, all right, but wait a minute, that would be if they move at exactly the same speed. This is like one of those math problems, though, where it's like, 2 trains, one leaves Baltimore and one leaves Boston at the same time. Which one of these two gases is going to diffuse faster? We have 17 grams per mole versus 36.5 grams per mole. So ammonia is going to diffuse faster. So ammonia is going to move past 6, and they're going to meet up somewhere to the right of the middle. You can actually calculate what it is. I'll post an answer for it. But somewhere over here, I think it's somewhere right around 7 point something. I could tell you. It's about 7.1. All right, so the question is, why doesn't it go farther? NH3 doesn't move twice as fast. The ratio of their speeds is inversely proportional to the square root of the molar masses. So NH3 moves about like a little less than 1.5 times as fast. All right, that's it. I'm going to call it a day there.